Welcome to our video on the physics of elementary particles with the matter particles, leptons and quarks, interaction mediators, and the Higgs boson shown in the figure. Here we will discuss total and differential cross-sections. At start, we remember the idea of the total cross-section. A beam comes in from the left and hits a target foil with scattering centers. If a beam particle passes through the interaction region sigma around a scattering center, it gets deflected. Sigma is the total cross-section. We measure a total cross-section sigma by the scattered rate .n divided by the luminosity L. Here L contains the incoming rate .ns, the target number density n, and the target thickness delta x, which vary from experiment to experiment. We present the total cross-section as a geometric effective area, which reflects the microscopic size of the target particles. In quantum mechanics, scattering is a probability, but we still express it in units of area. Let's look more closely at cross-sections. The differential cross-section counts scattered particles just like the total cross-section, but only those that fly into a cone of solid angle delta omega around an angle theta relative to the beam. We measure a differential cross-section d sigma d omega, again be the counting rate .n, dividing by both the luminosity L and the coverage of a detector under the solid angle delta omega. That way we can study distributions of the scattering angle. Consider two incoming particles A and B that exchange a mediator and leave as C and D. An example is an electromagnetic interaction of an electron-muon scattering with photon exchange. In the center of mass frame of A and B, we study the scattering angle theta star at which C and D emerge. For exchange of a mediator, small angles around theta star equals 0 are strongly preferred, forward scattering. Backward scattering theta star equals 180 degrees is much rarer. This was already observed in the famous Rutherford experiment with alpha particles scattering off gold nuclei. If the two incoming particles are a particle and its antiparticle, they can annihilate into a mediator particle. One example is a positron and an electron annihilating into a photon, leading to a pair of a positively and a negatively charged muon. Here too we can study the angular distribution of the outgoing particles. For annihilation, the distribution of theta star is symmetric. Forward and backward are most likely, while 90 degrees is less likely. In comparison, exchange tends to favor forward scattering. Annihilation is symmetric. Such angular distributions reveal important details about the particles and the mediators involved. We saw how a total cross-section and a differential cross-section are defined. Differential cross-sections reveal the distributions of the scattering angle. For exchange processes of a mediator particle, small scattering angles are preferred. For annihilation processes, the scattering angles appear to be rather symmetric. Have fun with investigating the smallest structures in particle physics.